Alright, Ph261, Chapter 7, Homework Problem 7. So, here, what we have is a 2.25 kilogram particle moves from rest along the x-axis by an applied force from x equals 0 to x equals 9 meters. The scale is given by 7 meters per second squared. So the very top here, this is 7. So what we have is we have one right triangle and two right triangles. They're identical, they go to the top, and they have a base of 1. So what we could see this as realistically is one singular rectangle, because this one flipped upside down and slid along here would be one rectangle. So this is going to be the area here is base of 1. Let's see. Area from 0 to 5 is going to equal 7 times 1 plus. It's going to be 1, 2, 3 rows going up to 7. So it's going to be 3 times 7. So this one's going to be, let's see, 21 plus 7 is going to be 28. And we know that work in terms of this graph here would be equal to the mass times the area under the curve. So if we know the mass is 2.25, we multiply this by 2.25, and we get this times mass equals 63. So that's the work here for A. Now for B, it says to 6. So what we would do here is, this is a, just right here is a right triangle. And what we do is we would do 1/2 base times height, and the base is 1, and the height here is negative 7. So base times negative 7, that would be negative 7 over 2. So we would do 28 and subtract this. So that would be 49 over 2, which would be 24.5 times 2.25, because mass times the area. And we get 50, let's see, we get 55.125. So now the area from 0 to 6 equals 1/2 base times height. And we're going to subtract it from A5. So it's going to be subtracted from, or I guess we would actually do it the other way. We would subtract this from this. So I will rewrite it that way. It would take some time, but I think it's more correct. So this is actually going to be, A 0 to 5 minus 1/2 base times height of this, which equals 24.5, and then times mass. It's going to be 55.125. This is going to be the work. We times mass. Just trying to kind of fit it all in. I'm running out of space. And then we do the same thing for x equals 9. Now from here, it's not quite the same as this. However, we are going to have the 7 times 1, since we have two, as pointed out from above, two right triangles with the same base. So now, A from 0 to 9 equals, from here I will do A5, and then I will calculate this as 1, because it seems easier to me than to calculate it the other way. So it's going to be A from 0 to 5 minus 7 times 1. Just want to separate this really quick. 7 times 1 plus let's see, that would be 2 times 7. So that would be 14 plus 7. That would be 21. And now if we take 28, subtract 21, we're left with 7. And now we're going to times this by mass, times 2.25. And that gives us a work of 15.75. That looks it looks a little bit bad. Let's just do a very, very long 1. Actually, if I do this, it looks like I intentionally did that. So there. Now we have work is 15.75. Never mind. I'm not even going to fix. Here we go. Just redo it. It's a mistake. 15.75. Okay. So this is the area here, and area here, and then mass, or work. I apologize. Work is here, and here. So that settles this part. Now we have to figure out this part. Now how do we do this? So if we, the area there, speed's going to be what is the particle's speed and direction when it reaches the following points? (28) divided by Let me quickly take a look at my notes. Okay, so if we know that work equals the change in kinetic energy, that is what work is, and we also know that kinetic energy equals 1/2 mv squared, then from here we can actually figure out the velocity here, or the speed. Now we figured out the work in each of these scenarios. So at 5, we know how much work has been done. So what we could do here is we could substitute this for this. And we can now say that work equals 1/2 mass times velocity squared. Plugging this in for, let's just say, starting here. Give ourselves some space. we're going to have D. We're going to have, we said that for 0 to 5, our work done is 63. We have 63 equals 1/2, and our mass is 2.25 kilograms. V squared. What we can do, we can take half of this, so 2.25 divided by 2. We have 63 equals 1.125 V squared. Divide both sides by 1.125, so 63 divided by 1.125 is 56. 56 equals V squared, square root both sides. And we get velocity equals 7.48. Okay, that's D. And the direction, speed is, well, it's positive. I would like to say, because it's moving this way, the change here is always kind of moving towards this direction. It's showing that. I'm not entirely sure what a backward direction here would even look like, to be honest with you. Negative acceleration here. If you're negatively accelerating, you're probably going backwards, but well, let's keep figuring this out. Because here it's not quite past the line anyway. It's at zero acceleration, but I don't know if that would be considered negative. So that's D. Now let's try E. This is to 6. The work at 6 is 55.125, and since we know that half of this, we're going to just skip that step. So now half of the mass is 1.125. Now divide 55.125 by that mass, 1.125, and we get 49. Equals V squared, square root both sides, and we get, well, 7. I have it written down as 6.99. I'm hoping that 7 is accurate enough. My mistakes if there was an error, but it looks to me like this is very, very, very close to being correct. It might be a rounding mistake. Okay, so now that we have E, we might have room for F. And the direction, oh yes. Velocity of 7. I guess this is where we would know if it's positive or negative. That's a positive number, so I'm going to say positive direction. That's my justification. It could be wrong. And right here, we have work of 15.75 equals 1.125 V squared. 15.75 divided by 1.125, that's 14. Square root of 14. We have a velocity of 3.74. And of course, these are all meters per second. Meters per second. Meters per second. Okay. And these are all joules. There. So now that's everything answered. The direction of this also positive. Okay, there's the answer for that.